From the National Institute of Justice's Expert Systems Testbed Project Series, the following presentation is the Technical Capabilities, Concordant Study, and Examples. The NIJ Expert System Testbed Project, commonly referred to as the NEST Project, was launched as a technical assistance project to the forensic DNA community in May of 2005. The goals of the project are to evaluate the commercially available expert systems designed for the technical review of single-source data produced by forensic DNA laboratories, and to report the results to the forensic DNA community. This podcast represents the conclusion of the presentation, visual examples of rule firings in each system. Your presenter is Rhonda Roby, a technical consultant for the NIJ.
In this section, I will present common rules that you evaluate for single-source samples processed through each of the expert systems, including peak height ratios and low peak height. However, you will notice that as I go through these examples, certain expert systems further distinguish low peak height into low heterozygote and low homozygote. This is an advantage with expert systems because their sophisticated data analysis tools allow us to better define allele characteristics. For my first example, we're looking at a result from GMapper ID. As you can see, in GMapper ID, we have one rule that has fired. This rule is called PHR, or peak height ratio. If we look at the result from this D7 locus, you will see that the peak height for the 7 allele is much higher than the peak height for the 11 allele. We have set the peak height ratio amplitude threshold to be 50%. So we know by this rule firing that we have a result of less than 50%. When you look at the results from GMapper ID, you don't know what that peak height ratio is. You just know that that peak height ratio has fallen below 50%. With GMapper ID, you can provide other settings so you can get the peak heights associated with each of these peaks and calculate that peak height ratio yourself. Here is the exact same sample in FSSI cubed. We're looking at this particular locus where the results are 7, 11. You can see in the lower right-hand corner, the rule that is fired is PrefAmp AB. PrefAmp AB stands for Preferential Amplification AB. The A peak is the 7 allele that is much taller than the B peak, which is the 11 allele. So what FSSI Cube does is it provides the calculation and the information right here in a visual display, so you can see that this peak height ratio is actually 44.68%, which is below your 50% threshold that you used. Now we're looking at the exact same sample in True Allele System 2. You will see that True Allele System 2 has accurately made the allele calls, and a rule has fired. So if we look at the rule firings in the right-hand side over here, you'll see the listing of all the rules that True Allele System 2 has. If we blow up even further here, we can see that the relative height rule has fired. So in GMapper ID, we had a rule that fired that was called peak height ratio. In FSSI cubed, we had a PrefAmp AB rule that fired. And then in True Allele System 2, we have a relative height rule that has fired. These all are providing the same information, they just have different names to their rule firings. I'd like to just take a moment and just show a little bit more information on the True Allele System 2 display. We haven't spoken about this in detail. True Allele System 2 has 3 panels, as you can see. The top panel is you can see the allelic ladder with the actual sample overlaid on top of that. Here are the sample alleles seen here and here over the allelic ladder. The second panel is called a quantitation panel, and it has the relative height of the peak in a spicogram format over the allelic ladder. And then the third panel is just visualizing the alleles themselves. Another feature with cybergenetics True Allele System 2 is in this top section, where we can look at the particular allele calls that are made. So if I look at this 7 and 11, those are the particular allele calls that have been made in this sample. If I would like to change those allele calls, I can go in and modify that with this drop-down menu. Another thing to point out with True Allele System 2 is the priority. There is a priority that is associated with all the samples. So in running this sample through the batch of samples, if I had a whole bunch of samples that were processed through True Allele System 2, this is my top priority for this locus to evaluate. The reason this has received top priority, or priority number 1, is because you can see in the quality value to the right of that is 0. Since my quality value is low, then I am looking at this sample, and it has passed through all the other samples that have met all the laboratory-defined criteria. Another area I'd like to focus you on is the area for the reject and the rules fired explain area. If I want to reject the sample, I can click that button. If I want to edit for some reason, I can actually edit the allele call, and then I can provide a reason. These reasons that are in the drop-down menu, are reasons that you have provided to cybergenetics that you commonly encounter when reviewing data. One last thing I'd like to point out are the scrollbar arrows. In this region here, there are arrows that you can scroll from sample to sample, or you can scroll from priority to priority. And with True Allele System 2, you can define this such that you skip from one sample to the next sample of low quality value to the next sample of low quality value. Once you have reached a sample that gives you a high quality value that meets your minimum requirement for quality values, then you would push on another arrow bar to take you to the next locus. Okay, let's look at our next example. This is an example in GMapper ID where we have low peak height. You can see in the display here that this particular allele has been called an 8 allele. You can also see in the left-hand corner the threshold, the peak height associated with this particular peak is approximately 55 RFU. If we have set our peak heights to be above 100 and this is below, then what we're going to get is a flag that actually says low peak height. Because of this low peak height rule that has fired, we have a low quality value. Looking at that exact same sample in FSSI cubed, and we blow up on that particular locus, you'll see that the software has stopped us at the 8 allele for this particular sample. If we look over at the rules that have fired, you can see that we actually have a rule that's fired called low homozygote. With this expert system, we can set the threshold for a heterozygote and a homozygote, and the software will actually make a call appropriately for the fact that this is in fact a low homozygote result. So the threshold that was set for a low homozygote was 200 RFU, and you can see here that we actually had an RFU value of 60 RFU, so our rule has fired. In True Allele System 2, we have the same sample where it has appropriately called the 8 allele. But you can see in the rule firings that two rules have fired, low homozygote and low signal. So True Allele System 2 is telling you that it did not meet your minimum RFU threshold and that this is a homozygote result versus a heterozygote result. Okay, now we're looking at another example in GMapper ID of a sample in D5 S818 where the two alleles are present visually, but they're not called. The first allele, the 11 allele, has been called because it has met the minimum peak height threshold. However, the second allele is not being called because it is such a low peak height. The rule that has fired for this particular example is LPH, or low peak height. Due to this low peak height, we have now assigned an overall genotype quality with a yellow value or a medium value. Here is the identical sample in FSSI cubed. If you remember from the previous display in GMapper ID, we saw two peaks. In this particular example, we only see one peak. An incorrect call has been made here. However, a rule has fired and brought this particular locus to the analyst's attention, and the analyst can review the actual raw data and see that a second peak is there. So if we look at the rule that has fired, the rule firing is low homozygote. However, we know that this is a low heterozygote. Here's the same sample in True Allele System 2. In True Allele System 2, the low homozygote and low signal rules have fired. The software has accurately brought this locus to the attention of the analyst, and the analyst can see in the top panel that in fact 2 peaks are present, but the software has only made a call to the peak above the threshold. So if we blow up this region here in the top panel, you can see that actually 2 peaks are present and visualized underneath the allelic ladder. Once again, what has occurred here is that the peak heights are so low, the rules have fired, it has called it a low homozygote and a low signal, but the rule has fired such that it brings it to the attention of the analyst. In this section, I will present results commonly seen when too much DNA is amplified. We'll be looking at off-scale data and -A. In this example, in GMapper ID, we have a 9 allele in the TPOX locus that is off-scale, most likely due to too much DNA amplified. In GMapper ID, a pink bar is available for display to tell you when a particular peak is off-scale. This pink bar can be visualized in all colors at that same location due to this particular allele being off-scale. This can call to the attention of the analyst spectral pull-up that we'll be discussing later on. What you will see here is that we have an off-scale rule that has fired in this particular example. Another important feature with respect to GMapper ID is that the off-scale information is from the data collection software. When the CCD camera has been saturated with color signal, then GMapper ID is able to correctly tell you when in fact the CCD camera was saturated. This cannot be seen in True Allele System 2 and FSSI Cubed. Here is the same sample in FSSI Cubed. You'll see that this particular allele, the 9 allele, has been called accurately. Over in the rule firings, you'll see that the particular rule that has fired is high signal, and that the threshold set for high signal here has been set to 9,000. The 9,000 RFU threshold is defined by the laboratory in the rule settings for FSSI Cubed. Here's the same sample in True Allele System 2. You can immediately see that the correct allele call has been made, but a rule has fired and brought this particular locus to your attention, and the rule that is fired is high signal. The high signal rule in True Allele System 2 is a laboratory-defined threshold. Our next examples, we're going to be looking at -A. In all 3 programs, you will find that the -A was correctly filtered and an accurate allele call was made for all systems. No rules for -A fired specifically in these examples. So in this particular example in GMapper ID, if we blow up this region, you can see that we have a peak here that has been seen by the software, but it has been accurately filtered and the correct allele calls have been made. Here's the same example in FSSI Cubed. Once again, we have the 8 allele being called, and you can see that, in fact, there is a -A peak that is visualized here, but once again, it has been appropriately filtered, just as in GMapper ID. Here's the exact same sample in True Allele System 2. In True Allele System 2, if we were to blow up this region, we can see the -A that is visualized here. You can see in this display, in the quantitation display, that in fact there is a small -A peak that is seen by the software system. But then when we get to the actual allele calls that are made, that -A peak has been appropriately filtered. In this section, I will present examples of how each expert system addresses microvariants, rare alleles, and trialleles. You will notice as we go through these examples that the different expert systems label these peaks with different flags, however the meanings are similar. Here is our first example in this section. In this example, we're looking at results in GMapper ID. What you will see in GMapper ID on this particular result is in fact that the 9 peak was named and there's an off-ladder allele that has actually been visualized by the software. The off-ladder allele is there because it does not fall on a bin. So this particular peak is within 2 bins that are defined in GMapper ID software. The rule that has fired is called out of bin. This particular locus is brought to the attention of the analyst, and the analyst can go in and manually make the correct allele call, which is a 13.1 for this locus. Here is the exact same sample in FSSI cubed. Once again, if we look at this result, we have a 9 allele that is called, and then there is a second peak that is visualized by the software system. If we look at the rules that have fired for this particular example, we have a signal to noise and an extra peak. These rules have brought this particular locus to the attention of the analyst, and the analyst can once again make the manual call that this is a 13.1 allele. In True Allele System 2, we can see that the 2 peaks are visualized. We can see that the particular rule that has fired here is off physical ladder. But you will also notice that in True Allele System 2, if we look at the allele calls that have been made, it calls the 9 13.1 alleles. This is the correct allele call. The 13.1 allele is the peak that you would have named in GMapper ID, and you would have named it in FSSI cubed. However, True Allele System 2 has accurately named this allele a 13.1. This locus is brought to the attention to the analyst because of the rule firing, but the allele call has already been made. Here's an example in GMapper ID of a microvariant. At the FGA locus, we have a heterozygote result. You can see here that, in fact, the correct allele calls have been made in 18.2 and 23. We're focusing our attention on the 18.2 allele. The 18.2 allele falls within a bin in GMapper ID. Since it falls within a bin in GMapper ID, you will also see that no rules have fired. If we look at this exact same sample in FSSI cubed, you will see that in FSSI cubed, we have it programmed to where it calls it an OL 18.223. The rule that has fired is the rares rule. The OL indicates that a true allele was within the rungs of the virtual allelic ladder. In this example, the correct allele calls have been made, and we have defined the software asking it to bring this particular locus to our attention because it is an off-ladder allele. Here's the exact same sample in True Allele System 2. In True Allele System 2, you'll see that the rule that has fired here is off physical ladder, but you will also see that the correct allele calls have been made in 18.2 and 23. In this example, we are looking at the results in GMapper ID. In GMapper ID, this particular result is an 11 greater than 16. That is a correct result, and you will see that no rule firings occurred with this particular example. In FSSI cubed, we have the same example, and you can see here that, in fact, for this locus, it accurately called it an 11 greater than 16. Also, you will see over in the rules firings that the rares rule fired here. The user has the ability to activate the rares rules. It was activated in this example. Here's the same sample in True Allele System 2. In True Allele System 2, you'll see that the rules that have fired here are off ladder, off physical ladder, and uncorrelated. The off-ladder rule and the off-physical ladder rules indicate that an allele is outside the largest rung of the allelic ladder. Uncorrelated indicates that the anodal shift of one allele does not correlate with the cathodal shift of the other allele in this locus. Whereas 3 rules fired, the software accurately called D5S818 an 11 greater than 16. In this sample, in GMapper ID, we see for TPOX we have 3 true alleles. The software has accurately called the alleles 8, 10, and 12. You can see in the rule firings that in fact we have one rule that fired, that is allele number, because we have set this for single source samples to be 2 alleles. Since there are greater than 2 alleles in this particular example, our allele number rule fired. For the same sample in FSSI cubed, you will see that the 3 alleles are actually visualized here. You can also see here that the designations that have been identified are the 8 allele, the 10 allele, and the 12 allele. The rules that have fired over here are the extra allele rules. In this particular example, we know that FSSI cubed has made the correct allele calls. However, FSSI cubed does not have a simple mechanism for handling trialleles. The analyst has to manually enter the third allele. In order to manually enter the third allele, the analyst has to go up in this corner where it has the A peak, which is the largest peak, the AB peak, and the B peak designation. And you would actually go in here and define the third peak for FSSI cubed. Here's the same sample in True Allele System 2. In True Allele System 2, you will see in the top panel that all 3 peaks are visualized. You will also see that in the rule firings that a third peak rule has fired. I want to bring your attention to the upper left-hand corner where in True Allele System 2, they have a designation up here that shows up when in fact a third allele has been called. In True Allele System 2, the software has accurately called all 3 alleles. The last example I'm going to provide is spectral pull-up. You will see in GMapper ID that multiple rule firings have been triggered in this particular example. In this example, I have the THO1 locus. The results are a 7, 9, but you will also see in the lower right-hand corner that I have an off-ladder allele. This off-ladder allele does not fall within a bin. If I look at my rule firings for this sample, you'll see that I have multiple rule firings, out of bin, peak height ratio, low peak height, spectral pull-up, and allele number. The third unlabeled peak is spectral pull-up from D13S317. Because of this third peak, all of the PQVs that fired are correct. The analyst can toggle to the raw data to confirm that this peak is due to spectral pull-up. Additionally, if you remember the pink indicator of off-scale data, we have the peak indicator turned off here. That would have been very helpful in identifying that this sample was actually spectral pull-up. Here's the same sample in FSSI cubed. You will see that in this sample, the correct allele calls have been made a 7 and 9 allele. You'll also see that the peak that is also seen here is at the exact same location of the 11 allele. If we look at the rules that have fired, we have 3 rules that have fired: signal to noise, extra peak, and pull-up. The pull-up peak rule has fired because it is at the exact same location of the D13S317 allele. Here's the same example in True Allele System 2. In True Allele System 2, you will see that the 2 alleles have been accurately called. You'll also see in the rule firings there are no rule firings for this particular example. I also want to bring to your attention the results in the top panel. You will see in this top panel that in fact there is a peak that can be visualized here, which is that spectral pull-up. But the software has accurately filtered that particular peak out of the display in the lower panel. If we look at the alleles that have been called, it has accurately called this locus a 7-9. We hope that this presentation has provided you with an overview of the NIJ Expert System Testbed Project, the evaluation we performed on the 3 different expert systems, and our concordance results. The concordance information that we have presented demonstrates that each software program or set of programs functions as an expert system as defined by this project and produces correct allele calls and appropriate rule firings. Whereas we have highlighted some of the rules that have fired in samples that require human review, I want to emphasize that an expert system allows you to only focus attention on those results that do not pass through your laboratory-defined criteria. What this means for your day-to-day operations is very important. If you have good quality data the majority of your convicted offender DNA profiles will not require human review. If you have poor quality data, you may experience more rule firings in your expert system, which will most likely require more human review time. One area we have not discussed in detail is the optimization process of each of the expert systems. This is a critical process in customizing the expert system for the data generated by your laboratory. Each expert system in this presentation requires some level of optimization that can increase the efficiency of data review and accurate allele calling. We hope that we have highlighted some of the unique features and rule firings of each of the expert systems evaluated. We encourage you to seek out more detailed information from the vendors of these expert systems. We also encourage you to visit dna.gov for the latest information on the NEST project and expert systems. On behalf of the NEST project team, we want to thank you for your interest in expert systems.
The content of this podcast was funded by the National Institute of Justice, which is part of the Office of Justice programs within the U.S. Department of Justice. The National Institute of Justice, or NIJ, is the research, development, and evaluation arm of the U.S. Department of Justice. NIJ has numerous programs that support state and local crime laboratories across the country.